This is Maryam Solaiman, and our research is about modeling, unlearning, and relearning with multi-agent Q-learning systems. So to provide an overview, our model centers around a Q agent, which uses the reinforcement learning Q-learning algorithm, representing a real-world learner, playing the game of NIM against different adversarial agents to learn the optimal NIM strategy. When the Q agent plays against a type of adversarial agent, specifically suboptimal agents, its percentage of optimal moves decreases. We call this unlearning. To mitigate unlearning, we experimented with modulating. To mitigate unlearning, we experimented with modulating the Q learning to ensure that minimal learning occurs with untrusted opponents. Our findings using this mitigation strategy allow us to parallel human trust, which decreases with untrusted opponents. Using the mitigation strategy, we observed that the Q agent with a baseline optimal strategy is able to robustly retain previously learned strategy. To model the opposite phenomenon, relearning, we run three-phase simulations where the Q agent plays against optimal agents in the first phase, suboptimal agents in the second unlearning phase, and optimal or random agents in the third phase. We find that even after unlearning, the Q agent is able to relearn most of its knowledge about the optimal strategy for NIM. To take a few steps back and break it down a bit, we'll start by introducing the game our model centers around, the game of NIM. NIM is an ancient Chinese game that involves a set of piles with some number of stones in them. Two players take turns removing stones from a set of piles, and the player to remove the last stone wins. NIM is a combinatorial game, and it's also impartial, which means that all players have the same available moves, which is important to use for our modeling misinformation simulation. Q-learning is a type of reinforcement learning, and the way we incorporate it in our simulation is by having a Q agent store its strategy to play NIM in a Q table. Its Q table describes the estimated total reward for taking a specific action from a specific state across all states and actions. So in our model, the states would be the states of the stones during the game of NIM. Based on whether it wins or loses the game, the Q agent can update its Q table with positive or negative rewards. By playing many games, the agent's Q table can converge to the optimal strategy. So since we're modeling misinformation, we must have a misinformation analogy. So the truth in our model is represented by the optimal strategy to win the game of NIM. Learners in our simulation are represented by Q agents with some initial beliefs trying to learn the truth by talking with each other or reading articles. True news is represented by agents which know and use the optimal strategy and do not learn. So these are called optimal agents. False or disinforming news is represented by non-learning agents, which use a suboptimal strategy. So the agents representing both false and true articles are called opponent agents. Conversations are games between the Q agents and our selected adversarial agents. So to reiterate, we have four types of agents. The Q agent is our learner, which constantly updates its Q table. The adversarial agents come in three types: the mal agent, which always loses because it plays by the suboptimal strategy. The optimal agent always wins a game by playing with the optimal strategy, and the random agent plays with random moves. So our Q agent would play against these different types of agents to try to converge to the optimal strategy. So our goal with this research was to find out that after periods of learning and unlearning, how much information can a Q learning agent retain? So for our methodology, we used multiple Q-learning agents playing against different opponents in a simulation for many episodes. Our Q-learning agents are all parameterized as suggested by Eric Jarlberg's thesis, which is listed in our citations. So we have an exploration rate of 0.1, a discount rate of 0.1, and an initial learning rate of 0.1. And the Bellman equation as shown below is used to update the Q tables of these agents. By adding a modifier that subtracts the predicted Q value of the future state, we improve the convergence rate for the Q learner. So our first experiment involved a learning phase with optimal agents and an unlearning phase with maloptimal agents. In our two-phase simulation, we had a learning phase and an unlearning phase, which is in contrast to our three-phase simulations. So for our learning phase, we play only optimal agents, and we have an accuracy, which is described by the percentage of optimal moves of 1, as you can see in the first graph. For the second half, it only plays maloptimal agents, and the accuracy in the first graph drops to 0.6. There is a significant drop in accuracy because the Q agent essentially rewrites its Q table with suboptimal strategies. So to mitigate this, we modulated the learning rate. So if the opponent's action was not the action that the Q agent would perform in that state, so if the opponent's action and the action for that state did not match, the learning rate is scaled by a multiplier of 0.1. So essentially, the Q agent judges its opponent's actions against its own Q table. And for the effects of this, we can see that without the modified learning rate strategy, the maloptimal agents cause the Q agent's accuracy to drop from 1 to 0.7 as it rewrites the Q table, signifying unlearning, which we can see in the first graph. By giving less trust to differing opponents, thus judging them, the Q agent achieves a stable accuracy of 1, as we can see in the second graph. Since it's playing a maloptimal agent, it has a high win rate in both cases, in the second case, but it does not have a high win rate in the first case since, let's see. In our second experiment, we had a learning phase with optimal agents and an unlearning phase with random agents. When it plays against the optimal agent in the first half, it has a high accuracy of around 1 and a low win rate. During the unlearning period, the Q agent is able to sustain its accuracy of 1. Since it's playing against a random agent, it also has a relatively high win rate. The main difference between playing against the maloptimal agent and playing against the random agent, so essentially between our experiment 1 and experiment 2, is that when playing against the random agent, the win rate is exactly the same as the accuracy rate. This is due to the epsilon or learning rate, which randomizes our actions. So it introduces a point of randomity that causes the win rate during random agent games to be only as high as the agent's moves themselves, while this is not a problem when playing against the maloptimal agent, which always loses. Our third experiment was also a two-phase experiment, and in our first half, we have random agents, and in the second half, we have optimal agents. So for the first half, the agent plays against a random agent, which results in a low accuracy of around 0.6 and a win rate of around 0.8. For the second half of the training period, the agent plays against a random agent but implements the scaled learning rate strategy. So if the agent's move for a given state did not match with the Q agent's moves. Despite this uneven scaling for agents that have different suggested moves, the agent was able to learn from the optimal agent because the opponent agent always won and always played with the optimal strategy. Since it was playing against an optimal agent, its win rate was around 0.6 after originally plummeting, but its accuracy climbed to around 1. It learned slower using the strategy, but it still learned the optimal strategy. This was a little bit not intuitive since we had expected that the random agents in the first half and the optimal agents in the second half would change the results. In our fourth experiment, we had unlearning and relearning in 3 phases. So our first phase is a learning phase in which it plays with either an optimal or a random agent. Our second phase is an unlearning phase, in which it plays with a different agent than it played during the first phase. And in the last phase, we reintroduce it to an optimal or random agent in order to see how much of its previous moves it has retained or is able to relearn. So our first phase, learning phase, consists of 5,000 rounds where the Q agent plays against optimal or random agents. The second phase, the unlearning phase, consists of 10,000 rounds where the Q agent plays against maloptimal agents. And the third phase, the relearning phase, consists of 5,000 rounds where the Q agent plays against optimal or random agents again. The results show that the Q agent retains its knowledge of the optimal strategy even after unlearning and is able to relearn it much quicker than it had learned it initially. And our first graph shows an optimal learning phase and then an unlearning phase, followed by an optimal phase. Our second graph shows a random learning phase, followed by an unlearning phase, which is followed up by another random phase. And our third graph shows an initial optimal phase, which is followed by an unlearning phase, and it goes back to a random phase. So as for our results, we are modeling misinformation with a novel multi-agent NIM game and using Q-learning for modeling learning behaviors. So our current findings provide proof of concept that reinforcement learning agents do accurately simulate human actions. When simulated learners are more likely to learn from those that are similar to them, this can cause them to retain their knowledge of an optimal strategy, even in the presence of disinformation agents, which is similar to trust in human systems and can be reflected in reinforcement learning agents. Q-learning agents can often learn from those agents that are different from them, even if they judge against them, although at a slower rate, which shows that the modified learning rate strategy holds true even when it's playing against suboptimal or random agents. When simulated Q-learners are reintroduced to either random or optimal agents after a hiatus of about 1,000 episodes, they are able to pick up and relearn the optimal NIM strategy, which indicates learned memory.